very much.
Yeah, yeah. And now it's my very great pleasure to introduce my friend and colleague, Professor Roya Maboudian. She's, as you heard, professor in chemical engineering, Berkeley. She's also in applied science and technology and nanoscale science and engineering programs there. After her PhD at Caltech, she did further training at Penn State, where we met, and then at UC Santa Barbara. Since she's moved to UC Berkeley, she's won, among many honors, the Presidential Early Career Award for Scientists and Engineers from Professor Bill Clinton. She's a Changbai Mountain Scholar and part of the 1,000 Talents program at Shanghai Jiao Tong University. Today, she's going to tell us about silicon carbide micro nanosystems for harsh environments. Professor Maboudian, the floor is yours.
Thank you so much, Paul, and Alice for inviting me here and for that kind introduction. What I will do is to switch the video to improve the connectivity, since it's a little bit choppy on my end. Let me share. Can you hear me?
Yes.
Yeah.
Okay, so let me switch to the, can you see only the slides?
Wonderful.
Do you see the slides?
Yes.
Yes, okay, perfect. Thanks again, as I said, for inviting me to speak here. I'd like to share with you some of our research activities in silicon carbide, micro and nanosystems. The motivation for our research in this area has been to enable sensing in harsh environments. By harsh environment, we mean extremes of temperature, pressure, shock, radiation, and chemical attacks. What are some such environments? Looking at the energy industry, I have listed some of them here, ranging from oil and gas exploration to automotive engine to geothermal energy, to gas turbines and aircraft propulsion, along with the minimum desired sensing temperature and some desired sensing measurements, ranging from physical sensing, such as pressure, temperature, strain, to chemical sensing, such as sulfur, H2S, hydrocarbon, oxygen, and corrosion, and the rather extreme conditions of temperature, pressure, shock, and chemical attack. Our motivation is that sensing within these harsh environments would enable real-time condition-based monitoring of subsurface environments, combustion, and critical components. These, in turn, would lead to increased operation lifetime, improved efficiency, and reduced emission. And I should also add that the small footprint of sensors enabled by micro and nanosystems technology would ensure minimal impact on the overall operation of these equipments and applications. So we want to be able to do sensing in a variety of harsh environments. That's the motivation. As this audience knows, silicon is the dominant material in micro and nanosystems technology because of a number of reasons. It is the second most abundant element after oxygen. It has a stable, high-quality oxide that is easy to grow, and it has excellent electrical and very good mechanical properties. However, silicon has limitations. Its electrical properties degrade above 350 degrees C. Its mechanical properties degrade above 650 C. It is susceptible to radiation damage, and it is chemically reactive in many environments. So it suffices to say that silicon is challenged in many harsh environments. To address silicon's shortcoming, we've been exploring other materials, in particular, as you know in this presentation, that material is silicon carbide. Silicon carbide is a semiconductor whose electrical properties can be tailored by adding dopants, such as aluminum for p doping or nitrogen for n doping. Silicon carbide has many polytypes, basically different silicon carbide bilayer stackings. What does that mean? Let's look at 3C cubic stacking, starting with the bilayer A, as you see here in blue. The next layer would occupy the B sites, and then the next layer would occupy the C sites. And this would repeat ABC, ABC. Since there are 3 bilayers that repeat, it is called 3C cubic polytype. The other 2 most important polytypes are shown here, 4H and 6H. You see, for example, 4H, I hope you can see that 4H corresponds to stacking sequence of A, B, C, B, A, B, C, B. So now let's look at silicon carbide properties of relevance to this technology and compare them to silicon. The silicon carbide column, the third column, has the values for both cubic as well as the 4H polytype. The 4H polytype values are in parentheses. As we see, silicon carbide actually sublimes above 2800 degrees C, as opposed to silicon that melts around 1400 degrees C. Silicon carbide has a higher energy band gap, and so it is more radiation tolerant and electronically can be pushed to higher temperatures. Silicon carbide has a higher critical or breakdown field compared to silicon, which allows silicon carbide devices to operate higher voltages. Silicon carbide also has a higher thermal conductivity, and that's one of its key features when compared to silicon. And which, when we combine that with its wide band gap and higher breakdown or critical field, gives silicon carbide an advantage over silicon for high power applications. Silicon carbide also has a higher modulus than silicon and higher modulus to density ratio, which makes it an attractive material for high frequency MEMS application. Silicon carbide also is chemically, in particular in oxidizing environment, very stable, unlike silicon and even diamond, which fares actually rather poorly. So we can conclude that silicon carbide is a mechanically robust, chemically inert, and electrically stable wide bandgap semiconductor material. Given these characteristics, silicon carbide has been pursued and found applications for high voltage, high power, and high frequency applications, ranging from consumer products to automotive to other industries, including photovoltaics, in particular as inverters and converters. Essentially, all of these technologies revolve around single crystalline and epitaxial silicon carbide. However, for Microsystems application, polycrystalline silicon carbide, you will see me sometimes referring to it as polycarbide, comes close to exhibiting many of the key properties of crystalline silicon carbide, as I will show you, and has been the focus of our research activity in this area over the past 10 years or so. In particular, our activities in this area have included materials and process development, including deposition, etching, doping, and metallization, the development of microfabrication methodologies and microfabrication-based property characterization, and more recently, property enhancement via graphitization and nanostructuring, as well as several harsh environment sensing and energy applications that have become enabled by these advances. Each aspect has its own story. In this presentation, because of my limited time, I will focus on our work on thin film deposition, surface and interface characterization, and stabilization via solid-state graphitization, and one example in the sensing area that is enabled by these advances. I thought maybe this selection of topics would be of interest to the audience that is listening to me. Okay. Thin film deposition. Several methods exist for depositing silicon carbide thin films, as listed here, with their pluses and minuses identified. The one that we have focused on is chemical vapor deposition, CVD. Addition, chemical precursors are transported in the vapor phase to decompose on heated substrate to form the film. The advantages, in particular, of low pressure CVD, LPCVD, are listed here, namely high throughput and high film quality. Most earlier reports on silicon carbide growth have involved dual precursors. For example, silane as a source for silicon and propane as a source for carbon, requiring temperatures in excess of 1,000 degrees C. We have instead developed CVD processes based on single precursors, which carry both silicon and carbon sources. As an example, we have looked at this precursor, 1,3-disilobutane, DSP single precursor. We've been able to obtain polycrystalline cubic silicon carbide films at 750 degrees C, significantly lower than reported previously for silicon carbide growth. And we were able to deposit these films on a variety of substrates, including silicon and silicon dioxide. The crystallinity is confirmed by a variety of methods, for example, by X-ray diffraction, as shown here for growth on silicon 100, whereby we see the appearance of various silicon carbide peaks for growth, for example, in this case, for growth at 800 degrees C, with the dominant peak being silicon carbide 111, suggesting a highly textured film. The structure of the film was further characterized by transmission electron microscopy. For example, in this the right-hand cross-sectional image, the film clearly displays a columnar morphology with a strong 111 texture, as also confirmed by select area electron diffraction pattern shown. One of the important characteristics of this deposition process is that it is highly conformal, meaning it deposits well on vertical as well as horizontal surfaces. As you see from the fairly uniform film, silicon carbide film deposited on these high aspect ratio silicon microtrenches. Films as thin as 10 nanometer are pinhole free, as evidenced by the fact that the silicon carbide coated silicon parts can survive a very aggressive silicon etchant, namely hot KOH. The image on the upper right-hand side is that of a silicon cone drive resonator subjected to hot KOH, and we see it is completely gone, while the one below has 40 nanometer silicon carbide coating on it, essentially encapsulating it. We see that the device remains unchanged after immersion in hot KOH and was subsequently actuated with no changes in resonant frequency. Low deposition temperature is crucial here, without which we would have severe deformation of our structures. This also suggests silicon carbide application as a coating to ruggedize silicon microsystems. Next, this table shows that silicon carbide has much reduced oxidation rate in comparison to silicon. For example, upon exposure to 850 degrees C in air, after 100 hours, we have a much thinner oxide growing on silicon carbide than on silicon. In this table, you also see what happens to 100 nanometer of diamond-like carbon with very high sp3 content, which is completely burned after only 24 hours. The results that I showed you so far were obtained in a home-built CVD reactor in our laboratory, shown here, capable of processing a centimeter by centimeter sample. With these promising results, to move to the next phase of our research activity, we had to be able to deposit these films on larger substrates. This included the second generation LPCVD reactor, capable of processing 2-inch wafers, and then a third generation LPCVD reactor capable of processing multiple 6-inch wafers, which is currently housed in the Berkeley Nanolab. To aid with the process development, as we scaled up our deposition process, we collaborated with Professor Mazzi of Politecnico in Milan to develop a multi-scale reactor model, including quantum chemical calculations that were used to identify reaction pathways and their incorporation into a one-dimensional reactor model with axial dispersion to determine, among other things, the growth rate profile. Let me share with you some of what we learned from this combined experiment and modeling studies. Here you see a plot of experimental growth rates along sample length, basically along axial position in the center of the tube furnace for various growth temperatures, ranging from 650 degrees C to 850 degrees C. What we see is that at low temperature, the growth rate is lower, but is more uniform. At high temperature, it is higher, but it also decreases along the axial direction away from the gas inlet. Here, the simulation results in solid lines are plotted on top of the experimental data points. We see that the experimental trends are well reproduced by the model. Based on the model, it appears that the cause for this behavior is that we are dealing primarily with two reaction pathways. One, of course, is the adsorption of 1,3-disilobutane and its decomposition on the surface, yielding silicon carbide on the surface and hydrogen as gaseous byproduct. In addition to this, we also have gas phase reactions. The most important gas phase reaction is found to be the decomposition of DSP to this radical species that you see in red. Basically, it's a DSP molecule with the end silicon missing two of its hydrogen, plus, of course, a hydrogen. This radical species provides another effective channel for silicon carbide growth, in particular at high temperature. To show this, I've plotted here the concentration profile of DSP and this radical species along axial direction in the reactor at 650 and 850 degrees C. At low temperature, we find that it is the DSP adsorption that dominates, with a flat concentration profile consistent with a flat growth profile, thin film growth profile that we observed experimentally. At high temperature, it is the formation of this radical species that takes place more effectively, and because of its high sticking coefficient, it causes the growth rates to increase, especially at the beginning of the reactor hot zone, giving rise to the observed non-uniformity in growth rate at high temperatures. This understanding was very helpful to us when we scaled up the process to actually 6-inch wafers in an LPCVD reactor in our nanolab, shown schematically here. Among other things, we looked at two boat geometry, open boat geometry and closed boat geometry. And we were able to obtain fairly uniform films, shown here with purple, in purple symbols, by going to closed boat geometry, which basically allowed us to pinch off the gas phase reaction, the second reaction pathway. In addition to 1,3-disilobutane, we also examined two other precursors, namely methylsilane and methyltrichlorosilane, which have complementary characteristics to DSP, but because of the limited time, I will not discuss these today. And move to the next part. The as deposited silicon carbide films are highly resistive due to silicon carbide wide energy bandgap. We have been able to tailor its electrical properties by dopant incorporation, in particular by adding nitrogen to the lattice. This was achieved by flowing ammonia through the reactor during the silicon carbide film growth, so it's in situ doping. The results in this slide are for deposition at 800 degrees C. The figure you're looking at shows the resistivity of the film as a function of ammonia to DSP flow rate ratios. With the increase in this ratio, the resistivity drops by several orders of magnitude, then more gradually reaches a plateau around 30 milliohm centimeter, which is very respectable for silicon carbide, and especially at such temperatures. X-ray absorption spectroscopy suggests that the nitrogen is occupying the carbon site, as shown schematically here. Next is a plot of carrier concentration obtained by Hall probe measurements and nitrogen concentration obtained by secondary ion mass spectrometry as a function of, again, ammonia to DSP flow rate ratios. What we see is that with increase in ammonia flow rate, nitrogen and carrier concentration in the film increase. However, with increase in nitrogen content, the silicon carbide crystallinity decreases. We know that from X-ray diffraction. And this has an inverse impact on resistivity, which results in the plateau that we observe in the resistivity data on the left-hand side of the slide. The resistivity can be further reduced by post-deposition annealing. To be able to employ microfabrication techniques to silicon carbide to realize silicon carbide micro and nanosystems, we needed to be able to selectively remove it, to be able to pattern these films. This has been one of the major challenges with silicon carbide due to its strong physiochemical properties. Silicon carbide is not etched by most chemicals. Typical reactive ion etching chemistries etch silicon carbide much more slowly than conventional masking materials such as photoresist or silicon oxide or silicon nitride. So metal masks, for example, nickel, are employed, but metal masks are known to cause micromasking phenomena in which metal atoms of the mask material are sputtered by the plasma and redeposited in the etch field, producing brass-like features. For example, we could not do this in any of the RIE machines in the Berkeley Nano Lab. The metal mask also lead to contamination to the etch chamber and contamination to subsequent fabrication processes. Faced with this problem, we discovered that HBr, reactive ion etching, is very effective at etching silicon carbide over silicon dioxide and silicon nitride, yielding 20-to-1 selectivity, meaning this chemistry, this plasma chemistry, etches silicon carbide 20 times faster than it etches silicon nitride and silicon dioxide. And it results in a good sidewall profile, as shown here. So putting these results together, we've developed a silicon carbide microfabrication process analogous to silicon surface micromachining, starting with silicon wafer with silicon nitride isolation layer and polysilicon carbide or polysilicon ground plane. We proceed with the deposition of a silicon dioxide sacrificial layer and its patterning using CVD, then and reactive ion etching. Then we deposit our polysilicon carbide layer and pattern it using silicon dioxide mask, shown here, and HBr-based reactive ion etching. Then we remove the sacrificial silicon dioxide layer using hydrogen fluoride, obtaining freestanding silicon carbide microsystems. So using this microfabrication process, we were able to fabricate a number of microinstruments to characterize and optimize silicon carbide properties of relevance to microsystems technology. Some of these properties are listed here, ranging from mechanical properties such as strain gradient, to fracture, to electrical properties such as resistivity and contact resistance, to surface properties such as adhesion, friction and wear, so-called tribology. Each is an interesting story, but because of time, I will only discuss a few. In particular, surface characteristics with regards to adhesion, friction, and wear, as well as contact characterization, metal contact characterization. Okay, so interfacial properties. Unwanted adhesion, also called stiction, has been a major reliability concern in silicon microsystems technology, stemming from the fact that micro machines, microsensors have a large surface to volume ratio, and so surface forces dominate over body forces. Strong adhesion is also responsible for strong friction and wear of many micromechanisms. How can we quantify adhesion in this technology in microsystems? One method employs an array of cantilever beams. By bringing a beam in contact with the underlying substrate and measuring L sub d, the length above which the beam remain adhered to the substrate, we can calculate the work of adhesion, energy W, the energy needed to separate unit areas of two adhering surfaces, which you can show goes as L sub d to the fourth power, the detachment length to the fourth power. Let's see what happens when we go to silicon carbide in comparison to silicon. By going to silicon carbide, we see a significant reduction in adhesion. The numbers are shown in the table. For example, we see 1.5 millimeter long beam do not experience any adhesion, corresponding to an apparent work of adhesion in the microjoule per meter square range. This is to be contrasted to 200 micron polysilicon beams that remain adhered, corresponding to a work of adhesion, apparent work of adhesion of tens of millijoule per meter square. By combining the adhesion measurements with atomic force microscopy topographic analysis and X-ray photo electron spectroscopy chemical analysis, the weak adhesion that we observe can be traced to the following factors. The relatively rough surfaces of silicon carbide substrate, shown here, results in only a few asperities interacting when surfaces are brought together. Given the high hardness of silicon carbide, we expect essentially no deformation upon contact. Based on XPS analysis shown here, we also see essentially no oxide growing on as-released silicon carbide surfaces. So we are essentially dealing with two rough surfaces that primarily interact with van der Waals forces, resulting in the low adhesion values that we observed. How about wear? We have used this microinstrument, basically a beam rubbing against the post, and monitored how friction coefficient, static friction coefficient, varies as this beam is repeatedly rubbed against the post. This was in collaboration with Dr. Mike Duggar of Sandia National Lab. What we see is that under repeated contact, even a thin film of silicon carbide is quite effective, as shown in this plot of friction coefficient versus wear cycle of a, as I said, of a beam rubbing against the post. Without any coating, the device fails after 100,000 cycles, and we see wear debris and wear tracks. But with 40 nanometer silicon carbide coating, friction remains low even after 1 million rubbing cycle, and we see no wear debris. The next topic I would like to cover here is the silicon carbide metallization, or metal contact to silicon carbide. The stability and reliability of metal silicon carbide interface has been one of the key factors limiting high temperature and high power silicon carbide based electronics and microsystems. As an example, nickel is one of the most studied contact materials to N-type silicon carbide. However, high temperature annealing is needed to create an ohmic contact. But in the process, one is faced with carbon segregation on top of nickel, leaving defects and voids at the interface. There have been many approaches to develop more robust metallization schemes. These include multi-layer processes, which could get quite complicated. Also, the effect of interfacial chemistry on silicon carbide metallization is not fully studied nor understood. Furthermore, there are very few reports on metal contact to polycrystalline silicon carbide. To address these shortcomings, we've examined metal contact characteristics to other poly 3C silicon carbide. In this talk, I will only discuss platinum as the metal. We've used circular transmission line method, CTLM, for this interrogation. The top and side view of the device are shown, with green being the platinum and red being the semiconductor silicon carbide. By making current versus voltage measurements on CTLM devices with varied values, with different values of this gap D, we can calculate contact resistivity, rho C. Let me show you what we found out. Here, let's look at the results for direct platinum contact to silicon carbide. I've plotted here contact resistivity versus annealing temperature for annealing in air for about 5 minutes. What we see is that as deposited contact shows ohmic characteristics, but it degrades, it increases readily upon exposure to elevated temperature. Clearly, this is not adequate for high temperature applications. To enhance the stability of this contact, we examined the effect of solid-state graphitization of silicon carbide. The process is schematically shown here. By high vacuum annealing of silicon carbide, we can graphitize it. Basically, silicon preferentially desorbs. This is confirmed by Auger electron spectroscopy, where we see an increase in carbon to silicon ratio. You can see that when you compare the red curve to the black curve before graphitization. We can also confirm that by the appearance of G and D peaks in Raman spectra, the red spectrum. After graphitization, platinum is deposited and patterned, followed by oxygen plasma to remove the exposed graphitic layer from that gap D. The contact resistivity results are shown here again as a function of annealing temperature for 5 minutes in air. What we see is that platinum graphitized silicon carbide contact, the red data point, is more stable, exhibiting little change with temperature. X-ray diffraction spectra taken after annealing to 540 degrees C in air are shown to the right-hand side. We see that the direct platinum on silicon carbide sample, the upper green spectrum, shows various platinum silicide phases showing up, while no platinum silicide phases are observed in the sample with the interfacial carbon layer. So the presence of this interfacial carbon layer seems very effective at preventing the reaction between platinum and silicon carbide to take place, resulting in a more thermally stable contact. These are for 5-minute annealing. Now, what happens if we do extended annealing at elevated temperatures? Here are the results of contact resistivity versus annealing time at 450 degrees C in air. As you see, the contact resistance of the sample with interfacial carbon, the mustard color data points, eventually increase. Our analysis using Raman spectroscopy, as an example, indicate that we are basically losing this interfacial carbon layer, allowing the interfacial reaction between platinum and silicon carbide that we were trying to prevent to occur. To improve the long-term stability of our platinum silicon carbide contact, we coated the samples with a very thin, but 10 nanometer film of alumina using atomic layer deposition, as shown here in the bottom schematic diagram. The aim was that the alumina layer would serve as a diffusion barrier, preventing oxygen from interacting with our interfacial carbon layer. And as you see on the right-hand side, the green curve obtained on the alumina passivated contact shows a stable contact performance for the entire target time of 100 hours of annealing at 450 degrees C in air. Our detailed studies, some of which I shared with you, indicate that this interfacial carbon layer acts as an effective diffusion barrier to prevent interfacial reaction at high temperature. And the alumina coating protects this interfacial carbon layer from being damaged by oxygen penetration during high temperature operation. And overall, this appears to be an effective approach to stabilize platinum to silicon carbide contact for high temperature operation, high temperature applications. These advances have allowed us to tackle a number of harsh environment applications. Let me show you some examples now. These include strain sensors for structural monitorings that can operate from room temperature to 600 degrees C, thermionic energy converter to turn heat directly to electricity. Here you see silicon carbide cathode running stably at 2000 Kelvin, and a supercapacitor energy storage device that can operate at 500 degrees C using silicon carbide nanowire, which I didn't get a chance to share with you, and YSC solid electrolyte. And strain sensor that was subjected to 64,000 G shock without damage or shift in resonant frequency. Silicon carbide implantable electrode array towards a more reliable neural implants. Here we are leveraging silicon carbide's chemical stability in bodily fluid and the fact that it's more biocompatible than silicon. And most recently, we have used a silicon carbide platform for chemical sensing under harsh environment. Let me share with you one of these applications in more detail, namely in the area of gas sensing. In recent years, there's been a resurgence of interest in gas sensing in a number of areas, ranging from industrial process monitoring to air quality monitoring to emission control and breath analysis. As you might be able to see this market report projecting a strong forecast in the gas sensing area. Let's look at one example, combustible gas monitoring, as an example of industrial process monitoring. Combustible gases such as methane, propane, or hydrogen can burn when their concentrations reach a certain value in air, so-called lower explosive limit, LEL. It is critical to have appropriate detection for industrial safety and environmental monitoring. Current wired systems are difficult to install and expensive. Battery-powered wireless monitors would eliminate this installation burden, but the power requirement for current combustible gas sensors are too high to allow completely wireless combustible gas detection. One such sensor is a calorimetric sensor, whereby the presence of the combustible gas of interest causes a temperature change in the sensor due to the heat of combustion that I've highlighted in red in this equation. One commonly used realization of such a sensor is called a polyester, consisting of a platinum wire coated with a porous alumina coating that has platinum nanoparticles dispersed on it. The platinum nanoparticles, as you may know, have high activity for hydrocarbon oxidation. The heat of combustion that is produced causes the temperature of the platinum wire to increase, which in turn causes its resistance to increase due to platinum's positive temperature coefficient of resistance, TCR. As I mentioned, one of the main limitations of this kind of sensor is their high power consumption. For example, in this case, is about 0.5 watt. One approach we have taken is to leverage advances made in miniaturization through microfabrication methodologies and high surface area nanomaterials to achieve enhanced sensing performance. In the context of what I've just discussed, industrial process monitoring, microfabricated heaters allow us to reduce size and lower power consumption while having a scalable, cost-effective, and reproducible production process. Advanced sensing materials provide us high surface area, resulting in enhanced sensitivity. They also provide us opportunities for enhanced selectivity and stability. Let me go into a bit more detail, starting with microheater, micro hot plates, if you wish. Our microheater is shown here. It is basically a polysilicon carbide, and for comparison, polysilicon heating element embedded in a silicon nitride membrane that we can fabricate using the process flow I described to you earlier in my presentation. Semiconductor materials such as silicon carbide and silicon, as opposed to metals such as platinum, have higher resistivity that is tunable with the doping level. Again, I showed that earlier in my presentation in the context of silicon carbide. This allows for more efficient heat dissipation in a smaller area. We've used a suspended membrane in order to reduce heat loss to the substrate. Here, you're looking at an optical image of the entire microheater chip. It's 3.5 by 3.5 millimeter with 4 microheater elements, basically 4 sensors. Next, you're looking at one of these microheaters showing the sensing and heater electrodes. And here you can see the lateral dimensions. The heater trace has a width of about 10 micron and a thickness of about 100 nanometer in a silicon nitride membrane with a thickness of about 200 nanometer. And here you're looking at an optical image showing the microheater heated to glow point that we use for temperature calibration purposes. Here I'm showing you some of the data obtained that we obtained for both silicon carbide and silicon microheaters. The silicon carbide microheater has somewhat of a higher power requirement to reach 500 degrees C. As you see here, 20 milliwatts versus 15 milliwatts for silicon, which we attribute to the higher thermoconductivity of silicon carbide compared to silicon. The temperature coefficient of resistance, TCR, for the two heaters are also listed here, since we exploit TCR for combustible gas sensing. We see that silicon carbide has a higher TCR value, making it a more sensitive transducer for catalytic gas sensing, as I will show you in a few minutes. How about the long-term stability of these heaters? As you see here, when both heaters are powered to 500 degrees C, silicon carbide heater exhibit much lower drift than silicon microheater. During catalytic gas sensing, the heat of combustion leads to an increase in the heater temperature above, let's say, the baseline of 500 degrees C. To simulate this, we have applied a set of temperature changes between 10 and 250 degrees C above the 500 baseline to these microheaters. The middle figure shows what happens to the silicon, or how the silicon microheater behaves, exhibiting major instability and histodependency. In contrast to this behavior, silicon carbide microheaters display no such instabilities, showing stable baseline recovery even after being heated to 650 degrees C. Now, let me turn to the choice of sensing materials. Two-dimensional materials are attractive for this application because they possess high surface area to volume ratio, translating to high sensitivity. Furthermore, they can be turned into three-dimensional aerogels. Aerogels are porous materials derived from a gel in which the liquid component of a gel is replaced with a gas. Aerogels possess high surface area per device footprint while maintaining many of the 2D properties. Here I'm showing you some characteristics of two such aerogels, namely graphene aerogel and boron nitride aerogel, with the boron nitride aerogel exhibiting much better thermal stability, surviving temperatures in excess of 900 degrees C. Furthermore, these aerogels can be functionalized, for example, with platinum nanoparticles shown in these transmission electron micrographs to enhance their selectivity to the analytes of interest, in our case, to selectively detect combustible gases. Once the aerogels are made and functionalized, then they are deposited on our microheater device to complete the fabrication of our chemical sensor. As an example, here you're looking at an optical image of the sensor before, bare sensor, and after the catalyst deposition, in this case, platinum-loaded boron nitride aerogel. Last, you see the sensor is wire bonded into a inserted package ready for testing. Let me share with you some results for propane sensing using our silicon carbide platform, functionalized with platinum-loaded boron nitride aerogel. As you see in the bottom plot, with the heater operating at 500 degrees C, we can detect propane in the concentration range from 5,000 to 20,000 ppm, which is great given that the lower explosive limit of propane is 2.1% or 21,000 ppm. So we can have early warning. As I projected, the plot shows that silicon carbide sensor is more sensitive than silicon sensor. Here you want to compare the triangular data points to diamond-shaped symbols. The power consumed by the silicon carbide microheater is about 20 milliwatts for the heater temperature of 500 degrees C. Given its a small thermal mass, we can also pulse the heater. For example, use 10% duty cycle and measure every second. And in doing so, the power consumption can be further reduced to 2 milliwatts. This corresponds to more than 2 orders of magnitude drop in power consumption with respect to many commercial combustible gas sensors. How about response and recovery times? Here you see the response to 2% propane and the sensor recovery. The response and recovery times are found to be quite fast, less than a second. Lastly, is a plot of the sensor response at 500 degrees C as a function of time. We see in green data point that the silicon microheater sensor shows a 15% drop in the first 18 hours, which we attribute to the instability in the polysilicon microheater resistance at these high temperatures. In contrast, the benefit of using silicon carbide microheater, the purple data point is clear, exhibiting stable sensing characteristics over the examined period of 36 hours at these temperatures. This approach of integrating silicon carbide microheater with high surface area nanomaterial seems very promising for robust, low-power gas sensing application in harsh environment. I would like to summarize my talk. I hope I have been able to show you that we've made significant progress in silicon carbide material science and process development, paving the way for the realization of a variety of harsh environment devices. I'd like to end my presentation by acknowledging the graduate students, postdoctoral scholars, and my collaborators, as well as Berkeley Sensor and Actuator Center and the Berkeley Nanolab for their key contributions over the years. I'm also grateful to the funding of the following agencies through the years. I stop here. Thank you for your attention, and I'll be happy to answer any question you may have. Thank you.
Thank you so much. Oh.
So let me switch.
There, I think the wrong image is up on the video there. If Alice's staff can put me up there. Well, that was a wonderful talk. While we wait for the questions to come up, I had one, and that is, what capability would you like for silicon carbide that you don't have yet? Right, the silicon's been so elaborated by industry over the years, and so you have sort of proof of principle of what it is that is possible essentially, and then also what the challenges are. What is it you'd be looking for now?
So thank you, great question. Of course, in one direction, we are pursuing these applications that are enabled by these advances. As I mentioned, for example, chemical sensing in harsh environment. On the material side and capability side, we would very much like to also be able to deposit higher quality materials, getting closer to electronic grade materials. And that would require, among other things, reactors that can go to higher temperatures than the one we have access to. So we are working on that. And the other thing that I didn't get a chance to talk about is that silicon carbide is also a very exciting photonics, from photonic point of view, a very exciting material. And so there again, for those applications, we would need a much higher quality silicon carbide. From the micro sensor point of view, as I mentioned, polycrystalline silicon carbide is for example, it exhibits very similar elastic modulus to single crystalline silicon carbide. But for these other applications, if you're looking at silicon carbide photonics, then you need much higher quality and much better control over defects, for example, and the kinds of defects we have. So those are some of the, on the more material side and processing side, some of the things that we are interested in.
Fantastic.
Did I answer
quite a
question?
Yeah, we have quite a number of questions from the audience, but I'll also follow up with some more of mine later, if that's okay, if we have time. So, Professor Maboudian, single or polycrystalline silicon carbide is a great material with excellent properties. However, if you grow at a low temperature, how is it possible to control the quality of thin films? How do you achieve high purity? Really related to what you were just describing.
Thank you very much. A very good question. It's a compromise, of course. There are pros and cons. What we find out is that using the single precursors that I showed you, we can get polycrystalline silicon carbide with of course, it depends on the quality of the system you have, the quality of the reactor you have, the cleanliness of the reactor you have, etc. But within what we have, we are depositing very clean material, and we can tailor the crystallinity by changing various process parameters, including temperature. To give you an idea, let's say if you look at disilobutane, if we reduce the temperature to 600 degrees C, the growth rate is very low, and we are depositing an amorphous film. As we increase the temperature, when we get to around 750 and 800 degrees C, then we create, the growth rate increases and we get polycrystalline material. And of course, I also showed you that we can actually, if you start with a brand new reactor and you do the process, the film that we deposit, let's say at 800 degrees C, are so resistive that we cannot even measure it, within the capabilities we have. And so, by adding dope, but of course you have to be able to tailor the electrical properties so you can, route signal and do things with the material. And so that we were able to do with nitrogen incorporation. Now it's interesting that once you do that, once you bring nitrogen to your reactor, after you remove it, you never get back the initial high value of resistivity. So in other words, there's some residual nitrogen that remains in the reactor and affects the electrical properties. So again, it's like I said, it depends on the temperature, depends on the cleanliness of your reactor. It depends on what it is that you want to do with it. How sensitive is the device, for example, that you're after? How sensitive is it to these parameters? I guess I should just end by saying that another approach for depositing carbide at low temperature is by, for example, plasma enhanced CVD. There, as you may know, it is very difficult to obtain the kind of quality film we have by the process I showed you, albeit at higher temperatures. I hope I answered your question.
Yes, I think so. The second question is, dear Professor Maboudian, great work. Silicon carbide etching is a big challenge. Could you share more details of your etching recipes and release steps?
Thank you. Indeed, that has been one of the major challenges. And given the kind of panel discussion we had before my presentation, I think this is kind of an interesting story. When we got to the point where we wanted to be able to pattern these films, we were basically stuck because we couldn't use metal mask in the Berkeley Nano Lab for the reasons I mentioned to you. But I had a very clever graduate student that said, let's try HBR, reactive ion etching. And it was available because HBR, reactive ion etching, is used for etching silicon. And interestingly, that was never attempted before in the literature. And then of course he discovered that it can be very selective to etching of silicon carbide over silicon dioxide and silicon nitride. And we can further tune that by adding chlorine to the chemistry, to the plasma chemistry. I'm happy to share the details, but it's also, if you just look up some of our publications, you will see the details of the etch chemistry that we have developed. So I think I would refer you to the publication because I think it's a little bit maybe too much nuts and bolt information for the audience. And of course, if you would like to contact me, I'm also happy to provide additional information for you. But we have published the work because of its novelty and the impact it had in pushing this technology forward. Thank you for your question.
And the next pair of questions are, do you use silicon carbide thin films as packaging materials for silicon-related devices, and how high a temperature can they endure?
Excellent question as well. It depends on what it is. What is the silicon device that you want to package? So we have actually used our process, so that would be at 800 degrees C, to package released silicon micro devices. That also is published work. So it was actually quite interesting because we were able to, in one process, do two things. One was to encapsulate the silicon parts, but also package it. So that is very much doable. In that particular case, the silicon devices could survive. The released silicon devices, it was actually based on epitaxial silicon, so it could survive the conditions, 800 degrees C deposition condition. Often, you have to kind of know what your devices are and what your criteria are. One of the things to watch for is that if you've already metallized your silicon devices, then depending upon the metallization scheme you've used, our temperatures are too high. And so there's again, depending upon the kind of quality you're looking at, plasma enhanced CVD might, if you cannot go to these temperatures, then you have to dial down, and so look at plasma enhanced CVD. Another approach is ion beam assisted CVD that has the advantage in comparison to plasma enhanced CVD in that you don't retain a lot of. One of the problems with plasma enhanced CVD is to getting rid of the hydrogen in the film, but with ion beam assisted you can address that problem. But then the film is amorphous, and so it depends on what you're trying to package and what kind of constraints you have, including temperature ceiling. I hope that answered your question.
Yeah, very good. The next question, which I didn't quite make it on the slides, as you've developed silicon carbide and the micromachining processes, do you think silicon carbide could be used for micromotors, turbines, and bearings to take advantage of the material's properties?
Absolutely. And as I also showed you, you can also, silicon carbide goes a long way as a coating to enhance silicon. So one could envision, for example, having micromotors that are made out of silicon, but they're ruggedized by using silicon carbide as a coating. And so this way we can leverage all the infrastructure that is being developed through, since the 70s, that have been developed around silicon. We can leverage that and then bring forth material like silicon carbide and enhance it. So yes, very much so, both as a thin film as well as a material itself. For example, the neural implants, it's all silicon carbide, or the chemical microheater is all silicon carbide. We've also published the use of some of these advances to obtain more robust micro gears, micro engines, and things as such. Thank you for your question.
Sure. And then the next question is the propane sensing with silicon carbide chips selective, and how do you achieve high selectivity for gas sensors?
Thank you. A very good question as well. So this is selectivity is one of the biggest problems in gas sensing. And so we achieve, in what I showed you, we achieve selectivity with platinum. If we don't have a platinum, we do our boron nitride aerogel senses nothing. When we have platinum nanoparticles loaded on it, we can take advantage of the combustion reaction. Then we see, so we need the platinum, and of course we need the oxygen, and that's how we can detect combustible gases. So this approach of look, and that's where I think also nanotechnology has a lot to offer, the ability to tailor materials, high surface area materials to achieve enhanced selectivity. So by using this combination of thermally stable aerogel like boron nitride and the platinum nanoparticles that have high activity towards hydrocarbon oxidation, we can become very selective to detecting combustible gases. So we don't detect anything else that doesn't combust. Now, of course, there are many things that combust. So, for example, hydrogen. The way we can differentiate the two, whether we have hydrogen or propane, is by changing the temperature of the heater. So, for example, hydrogen we can combust around 200 degrees C. Propane, we have to go to higher temperature, 500 degrees C. So that's the other knob we have. That's the other knob that is enabled by having a microheater that has a fast response and recovery time and can be pushed to these temperatures, is that we can use that to further differentiate amongst different combustible gases.
And final question, I'll take my prerogative as host to ask, how developed is the surface chemistry, my own favorites, how developed is the surface chemistry of silicon carbide?
In comparison to silicon, not as much. And that I didn't get a chance. That's been also of interest to us. And of course, the other challenge is that as you're trying to, extend this material to applications, it becomes more challenging from a surface science point of view to study. For example, the films that we have are rough. And then through time, the history of the reactor changes, and so basically, coming from a tradition, myself, the tradition of ultra high vacuum surface science on well characterized materials, to extend that to silicon carbide, there's a lot of room there. Part of the challenge is that to what extent doing those measurements can be tied back to more realistic conditions that the material is asked to do in these various scenarios, application scenarios. So I don't know if I answered your question, but so there are some, there's some similarities between ET and silicon, but it's also very different depending upon what phase of silicon carbide you have, whether it's silicon phase or carbon phase. You have very different surface chemistry. So we know a lot, but in comparison to silicon, it's still a lot of room to understand and tailor the surface properties of silicon carbide.
You have your work cut out for you.
Was I cut out?
No, I said you have your work cut out for you.
Yes.
Developing these applications and chemistries and devices, and it was just a wonderful presentation and elaboration of a part of your efforts. And so we want to thank you. And this, under normal circumstances, we'd be giving you a plaque, and we'd get to see each other and on a stage together and go out to dinner. In in these unusual circumstances, I'm afraid we have just this electronic certificate, and we'll look forward to the day, hopefully in a few months, when we can see each other in person. But thank you for this fantastic presentation and for sharing your research with the world through the ICANX lectures. Thank you very much.
Thank you so much, Paul. I appreciate the invitation from you and Alice, and I look forward to seeing you in the very near future.
Yes, and yeah, please be safe up in the Bay Area with the fires.
Thank you. The same to you in Southern California. The same. Thank you.
Okay. Well, next week we have two ACS Nano editors, Professor Molly Stevens from Imperial College London and Professor Ali Khadim Husseini, now at the Terasaki Institute for Biomedical Innovation. It should be a fantastic pair of presentations, and I'm looking forward to the panel as well. Alice and I will host next week's lectures together. So, please set your calendar alarms to join us again, whether it's Friday evening in Beijing or Friday afternoon in Europe, or very, very early Friday morning in California. It'll be worth attending these talks. And I also wanted to mention that we have the second ICANX ACS Nano Rising Star Lectures coming on September 4th. And that'll be Yingying Zhang from Tsinghua, Zhang Liu from Nanyang Technological University, and Shelley Claridge from Purdue University. These should also be spectacular lectures, and so I'll get to see you each of the next 2 weeks. And thank you so much to Alice for organizing this amazing series. We have this growing community of lectures from around the world, and we will keep going. For the winter, we're going to switch to a somewhat shorter format with the as darkness settles over the northern hemisphere for a little bit longer. And so we've been mapping the calendar upcoming, and we think you'll enjoy very much the talks that we have planned for you. So thank you once again, and I believe that'll be it for for today's lectures, panel, and presentations. And again, I just want to thank our speakers and Professor Alice Zhang of Beida for setting these lectures up and for the wonderful presentations that we heard today. Thank you.